Hey everybody. So we have been digging into these sine and cosine functions, learning a little bit about their definitions, practicing evaluating, seeing how the different trig functions relate to each other. We're going to jump today into the graph of sine and cosine, and this I find is often very confusing because we've been staring at a graph this whole time we've been talking about sine and cosine, right? This graph of the unit circle. This is not the graph of sine and cosine. That graph of the unit circle is the tool we use to evaluate sine and cosine, right? Or the tool we use to define it, but it's not the graph of the function. So what is a graph of a function? Let's just review that quickly. When we talk about the graph of a function is, let's say it this way, the graph of the function f of x is the set of all points a, b, such that f of a equals b. Okay, so what exactly does that mean? Well, it's all the input-output combination, all the pairs for a function. So for instance, when we write f of x equals x squared, and somebody shows you the graph and says this is the graph of f of x equals x squared, what they mean is that if you choose a point on this graph, it's an input-output pair for this function. So for instance, 3, 9 is on the graph because f of 3 equals 3 squared, or 9. Or the point, I know I'm not to scale necessarily, negative 1, 1 is on the graph because f of negative 1 is negative 1 squared, or 1. But the point 1, 9 is not on the graph because f of 1 does not equal 9, right? So it's a set of points that are all the input and output pairs for the function. So let's do this for sine. Well, we'll do it for cosine, and then we'll see that sine is very similar. And I'm going to start by just getting some input and output pairs, right? So that's why the unit circle is here. I want to just remind us of the definition. That's where these pairs are coming from. But then we're going to plot those pairs on their own set of axes. So I'm calling this the t-axis, and this will be our cosine of t, right? Our horizontal and vertical axis. One reason this is often confusing is we talk about, right, the cosine is defined as the x coordinate here and the y coordinate is the sine, but then we often just make this other graph also have an x and y, and we're using them differently. They're two different sets of coordinates, and we really shouldn't be using the same names, though it's pretty common for that to happen. All right, so let's get to it. So let's just go through. These are just the values we have from the unit circle. So there's cosine of 0 is 1. Cosine of pi over 6 is root 3 over 2. And I'm going to give decimal approximations. I usually prefer just to keep things in their precise form, their exact form. But since I'm graphing, I want to have an idea of, I don't really have a good sense necessarily of where root 3 over 2 is on a graph, on a number line. Root 2 over 2 is about 0.71. Then we have 1/2, and then we have 0. Okay, so each of these should lead to a coordinate point, right? So let's just write down those coordinates. This input 0, output 1 is the coordinate 0, 1. And then we have the coordinate pi over 6 on approximately 0.87. And we have pi over 4 and approximately 0.71. And we have pi over 3 and approximately, it's bugging me that some are in decimals and some aren't, so 1/2 becomes 0.5, and then pi over 2 gives us 0. So let's just graph these points. Let me put one more scale on this. Let's just make 1 right there. Put in -1, about even. So that this is looking not quite even to me. It's bothering me. Let's put it down just a little more. I think it's more about there. That close enough. All right. So at 0, the output is 1. So our first point on the graph is at 0, 1. Let's see. I'll put in a couple more values of my scale. These are at intervals of pi over 2. So pi over 6 is about right here, and that's at 0.87, so nearly up at 1. Pi over 4 is about right here, going down a little bit. Pi over 3, we're pretty close to pi over 2 now. It's all the way down to 1/2, and then by pi over 2, it gets to 0. Okay. And if we were to do this for more and more points, we would see, we would start to fill this in, and what we get is a line looks something like this, okay, on that first section. Let's see what that's telling us, right? So in this axis, what we're on the horizontal axis, these are representing the angles we're putting into cosine, right? The t's that I've called the angle up here. So when we start at 0, and then the vertical axis represents the outputs that cosine gives us for that angle. So when my angle is 0, I'm at 1. That represents, we're right here on our unit circle. An angle of 0, the output is the x coordinate. So all I care about right now is the horizontal position on this unit circle. As the angle increases, as t increases, so imagine this terminal side that I've kind of drawn arbitrarily here. Imagine this laying on the axis and slowly opening up. What's happening to that x coordinate? It's getting smaller and smaller as we move along the unit circle to here, right? At each point along here, the x coordinate is slightly smaller. Forget about the vertical coordinate. Of course, it's going up, but we don't care about that because cosine only cares about the x coordinate. And that's getting closer and closer to 0 until the angle is pi over 2, and then it's at 0. And this graph reflects that. The outputs, right? This 1 here tells me that the x coordinate of on this unit circle is 1 when the angle is 0, and that x coordinate is getting smaller and smaller and smaller until we get to 0 by the time the angle is pi over 2. What's going to happen as we continue on? Now the x coordinate is going to get further and further negative, right? We're moving further to the left on that unit circle, and by the time we get to an angle of pi, we're going to be all the way down at an output of -1. And so I won't fill in all the points, but our graph is going to look something like that. Then we continue on from pi to 3 pi over 2. The x coordinate, again, we have to forget about what's happening vertically on this circle. The x coordinate is shrinking to 0, and by the time we get to 3 pi over 2, the output is 0. And so as we increase the angle, the output is increasing to 0. It started at negative and it's increasing, and as we move through that last quarter turn, we get back to a value of 1. So by the time we get over here, we're back to a value of 1. So the output, or the input here, is 2 pi and the output is 1. Okay. And we've completed a full turn of this circle. Okay, so I've graphed just one little piece of this cosine function. Okay. So what would happen if we were to continue doing this? So let's, oops, wrong thing. Let's get the pen. Let's move this out of the way. Let's add some, come on, there you go. Oh, it's making it thicker, but that's all right. What's going to happen if I continue increasing the angle? Well, let's go back to our circle. We're back where we started. And as we move further around, right, obviously we're still moving on the unit circle. I'm just drawing on the outside so we can see it. We're gonna spit out the exact same values. So as we continue to go, to move, let's see if I can do this. Here we're up to 3 pi. And let's call that 4 pi. So, oops, that's a 3. We'll increase our angle as we go, as we go through another quarter turn, we'll get to 0. By the time we get to a half turn, we're down to 1. Then we start to increase again. And we get back, this would be going around the circle twice. And the same thing would happen in the opposite direction, right? That would represent starting at 0 and going backwards. Our x-coordinate starts at 1, and as we rotate this way, the way I just drew this, the x-coordinate's decreasing to -1, increasing back to 0, and so this curve continues. And it goes on. We can just keep going around the circle and doing this forever. So pardon the horribleness of my drawing, but we now have a picture of a rough picture of the cosine curve, okay? So let's notice a few things about this curve, and then we'll take a look at the sine curve. So let me grab this drawing and let's go to a new page. It's not great, but I don't think I'm going to do any better. All right. All right, I don't need all that extra space over there. All right, so here's our picture of our cosine graph. I want to notice a couple of things about it. The first thing to notice, and this came directly from the unit circle, right? As we went around the unit circle, we get back to where we started and the graph repeats, right? So here's where we began. Here's where we went around once. Here's where we went around, by the time we went around twice. And every time we go around, you can see this graph just has to repeat because all we're doing is spitting out values on that unit circle. So if we keep going over the same points, the same values are getting spit out. So we have a name for functions like this that repeat themselves. So we call these periodic functions. Okay, and all that means for a periodic function is they have a period, which is a number. I'll call it p, so that f of x plus p is equal to f of x. Right. So all that means is if you put in a value, or you put in that value plus a constant, meaning you move the same distance over, those are always the same. P is the smallest such value for which that's true. So let's look at our graph and see what we have here. Notice we move a distance from 0 to 2 pi. Notice also that cosine of 0 is equal to cosine of 0 plus 2 pi, right? Because cosine of 0 is 1, cosine of 2 pi is 1 because we're at the same place. If we were to pick some point, let's pick a point in here. Let's pick pi over 4. This is the point pi over 4. It has the output √2 over 2. Well, over here, if we add 2 pi to pi over 4, so that's 8/4 pi plus 1/4, so this would be 9/4 pi. The output is exactly the same. Whoops, I drew that in the wrong place. There's my point. There is this other place where it's the same. We'll talk about that in a minute. Sorry, I just, that was not where I meant to draw it. This is the point there, and we'll look at the unit circle in a second and see where that comes from. This is 9/4 pi √2 over 2, right? This is just demonstrating the fact that the cosine of pi over 4 is equal to the cosine of pi over 4 plus 2 pi. Right? Again, we've moved over a distance of 2 pi. All right, and I could do it down here to here. This is a distance, right? Besides the fact that my drawing's not perfect, that's a distance of 2 pi. Okay, and whenever we do that, we're going to get the same value popping out of these, because each adding of 2 pi on our unit circle represents going around once. So the first one we did, we had the cosine of 0. Oops, I don't want to write that there. Right, this first, when we have an angle of 0, the output is 1. But if we go all the way around the circle, we have the exact same output. All the way around is 2 pi. If I'm right here, some angle, and I move all the way around the circle, adding 2 pi to that angle, I get back to the exact same spot, right? And that will always be true. Now, that little error I made where I drew the wrong one right there, that's the following happening. Let's look at this point here. If I add some amount of angle, remember we're talking about cosine, so there's an angle here and an angle here that have the same x coordinate. I know this drawing's getting awful, but we'll live with it for now. These have the same x coordinates, the same cosines, right? There's lots of places like this, right? So these 2 points have the same cosine. These 2 points have the same cosine. The problem with them is, there's no problem with them. The reason, though, those aren't the period of our function is because they're different at each value. The point of a periodic function is the period is this value that no matter what x coordinate you pick, adding the period to it gives you the same output, right? And so the fact that there's many spots where it repeats doesn't change the fact there's only that one smallest number, 2 pi, that always works, right? So whatever the distance between these two values is, that same distance doesn't work between these two values. The value that works for all of them is 2 pi. If you pick any point and move 2 pi away, you will get the exact same value. So cosine is going to be periodic with a period of 2 pi. Okay. We can also see, let's write that down. Cosine has period of 2 pi. You also might notice I kept saying it's the smallest number for which this works. 4 pi would also work as far as repeating if you go around twice, but we consider the period the smallest number that will always work to have this repeating property, right? That's when it actually repeats. There's no reason to skip one of the cycles. We can also see on this graph something we talked about previously. The range of this function is from -1 to 1. These peaks are all at -1. The valleys are all at -1. And I didn't draw it infinitely because I ran out of time. But we can keep drawing this forever in both directions, expressing that the domain is all real numbers. All right. So I want to look at a couple more things before we finish this. First, let's look at a little animation I found that might help us understand what we're looking at. So in the lower right corner here, we've got this green circle is our unit circle, okay? And so there's a little dot that represents the terminal point, the intersection of the terminal side of the angle in the unit circle, okay? Then coming out is, how do we translate these positions on the unit circle to graphs of sine and cosine? So let's look at the top one because that's the cosine that we did. Notice what this blue dot above the circle is doing. I'm pointing at the screen as if you can see where I'm pointing. So if you follow this blue dot just above the unit circle, all it's doing is keeping track of how far to the left or right that green dot on the circle is. And so the further right it is, the higher that translates into a higher output on our cosine graph. So that is translated vertically. And as it goes to the left, we get negative. And so you see that graph being spit out. The sine graph does exactly the same thing. It tracks that that green dot, except it's tracking the vertical, the y component, because sine is defined as the y coordinate of that intersection point. And so when that dot is higher on the circle, the graph of sine is higher. When the dot is lower on the circle, the graph of sine is lower. Cosine's a little trickier because when the dot is to the right, it's higher on the graph. When the dot is to the left, it's lower on the graph. All right, let's look at some nicer pictures of sine and cosine. So here are two graphs. The red is sine, the blue is cosine. Let's just look at cosine for a second. These are the points that I graphed for you by hand, those 5 points that I put in. And then you can see this graph, a much nicer picture of a graph than what I did. And notice there's that 2 pi, right? Going from 0 to 1, 2 pi to 1, we get the same value. Or let's see if it'll let me, won't let me pick, it knows to pick maximums, but right over here, if we go that same distance, there's a point with the same coordinate, right? And it goes on forever. If I zoom out, we see this cosine graph, right? It's harder to see now, but that up and down, that periodic motion continues forever. And let's add the sine graph, or let's look at the sine graph by itself now. Remember, the sine graph is tracking the y coordinate on the unit circle. So at an angle of 0, the y coordinate is 0, right? We're on the horizontal axis. As we increase the angle and we start rotating around the circle, the y coordinate increases. And so we start seeing that as the angle's bigger, pi over 6 gets us to an output of 0.5, pi over 4 up to 0.7, pi over 3 up to 0.6, until we're at pi over 2, where on the unit circle, our angle is straight up, so the y coordinate is 1. Okay? And so we can see that these graphs have kind of the same, I mean, they do have the same shape, they're just shifted because they're both, there's really nothing different about x and y on a circle except which direction you've decided to tilt your head. And so they're doing the same thing, just kind of starting a little different. Well, let's not get into the details there. So we've got sine and cosine. Notice both have a period of 2 pi. One last thing I want to notice is we mentioned in a previous video that cosine is an even function, and we can see that here, meaning it's a reflection over the y-axis, right? If you folded this paper in half, or the screen in half right on the y-axis, the graph would match up with itself perfectly, right? On the other hand, sine, oh, my pen is on my pad and won't let me move. Sine is an odd function. If we folded it over the y-axis, it does not match up, but in fact, it's opposite to itself. So one thing, if you imagine there's a hinge or a pivot point at the origin, you could rotate this whole graph 180 degrees and it would look precisely the same. Because we call it symmetric about the origin, and that's what odd functions graphs look like. So let me finish with a quick summary of what we've said. So we've got sine and cosine, the graphs. These two functions are both periodic with period 2 pi. They repeat every 2 pi. Their domains are all real numbers, negative infinity to infinity. You can also write this with this r, or we could say something like negative infinity less than x less than infinity. Those are just 3 different ways to write the same thing. The range is from -1 to 1. The brackets closed because we are including those. Y equals cosine of x is even. It's an even function. And y equals sine of x is an odd function. Okay, so those are some of the basic features of our sine and cosine graphs. In the next video, we're going to dig into some more details of what happens when we start messing with these graphs. But I want to just point out, reiterate something I said at the beginning of these videos. These things are really powerful for mapping things in the world that repeat: waves, heartbeats, orbits, seasons, that sort of stuff. And those graphs, you really start to see it, something that just keeps coming back to where it began. Okay, that is it for this one. Thanks, everybody. I will see you next time.